We will begin Module 4 on land use impacts and related best management practices with an overview of land use and how it affects water quality. We'll begin this module with a reminder of where we left off in Module 3, during which we discussed pollutant loads and yields and ways to reduce those values to meet water quality goals. In order to do this, you need to understand the contributing watershed, the prevailing land uses, and potential pollutant sources. Once you have this information, you can begin to identify and select the associated best management practice options that will help lower pollutant loading to receiving waterways. After today's presentation discussing the factors to consider in selecting appropriate BMPs, we'll go through examples that are used in different land use scenarios. These will include presentations on BMPs related to urban development and stormwater, agriculture and forestry, wastewater treatment, mining, and habitat improvement. And you'll note that education is a common theme that applies as a BMP for all of the above. In the formal watershed planning process outlined by the EPA, we'll be focusing on Step C of the A through I watershed planning criteria to describe management measures and targeted critical areas. Once BMPs are identified for these critical areas, you can begin to develop the following planning details: estimates of the technical and financial assistance you'll need, informational and educational components, a project schedule along with interim milestones, and a follow-up monitoring plan. As we have learned, many factors influence water quality as it moves through a watershed. It's affected by two basic categories of factors: the water itself, which is influenced by the climate and weather, as well as the hydrology, which refers to the properties, distribution, and circulation of the water on and below the Earth's surface and through the atmosphere, and hydraulics, or how the water flows within the stream channel. It also is affected by environmental influences, which relate to the physical setting into which the water flows through. This is affected by the geomorphology of the area, or the physical features of the Earth's geology, the land uses of the area, and the vegetation and organisms that are in a watershed and its water bodies. These topics were covered in more depth in Module 2, but in this module we'll be focusing on the environmental contributions of land use. The graphic provides a simplified illustration of some of the pollutants that could be located in your watershed based on the types of land uses. Factory wastes are likely to be piped point sources with associated discharge permits, but the others are all mainly non-point sources with only voluntary means of controlling them. In Module 3, we discussed how you calculate an existing pollutant load and compare it to a water quality standard or benchmark shown by the red line for healthy stream conditions. If the pollutant load is greater than this standard, you can determine how much the level needs to be reduced to achieve the criteria of a healthy stream. To assist with this process, we talked about calculating pollutant loads and yields using these equations. Loads refer to pollutant measurements at a specific point, and yields refer to pollutant amounts contributed by a land area. Since the yield is determined by dividing the total load by area, it accounts for that area's land runoff sources. We also talked about assessing incremental and total loads. Here's a visual of a watershed that illustrates these concepts. The incremental load of total nitrogen for the subwatershed, colored in green, is 12,000 pounds, whereas the total load for the entire watershed, including the subwatershed in green, is 22,000 pounds of total nitrogen. Since sub-watershed areas can contribute varying levels of the overall pollutant load, it's helpful to know their incremental yields for prioritizing management practices where pollutant reductions can be the greatest. Using our previous example, you can calculate yields for the subwatershed in green and for the total watershed area. If the subwatershed contributes 6,000 pounds of total nitrogen per square mile, whereas the overall watershed contribution is only 2,750 pounds, it appears that the subwatershed is contributing a higher yield than the overall watershed, and it may be a good area to address first. It's also a headwater subwatershed, so improvements may translate to downstream water quality improvements. If you are selecting BMPs, then you should ideally have a map of your watershed with load reductions that are necessary from each subwatershed area, as in this example from the Clark's Run watershed in Boyle County. The map provides needed pollutant reductions of nitrogen, human E. coli, and cattle E. coli for each of the contributing subwatersheds. This information has been very helpful in developing and prioritizing BMPs for implementation. For instance, the implementation activities have included septic system repairs and replacements. The coordinators of this program can refer to the human E. coli reductions needed in each of the subwatersheds to prioritize homeowner applications. This allowed them to see that Stanford Road, South 2nd Street, and the Balls Branch West subwatersheds should be prioritized. They have the greatest human E. coli contributions. Of course, there are many other factors to consider when making final prioritization decisions in your watershed area. In addition to land use and land cover characterizations, you'll want to look at geology and soil. Is the geology favorable for karst formations that may allow for underground pollutant flows into or out of the watershed area and therefore make pollutant reductions difficult to predict? Is the soil type easily erodible and likely to contribute to loading? Or does it allow for slow or fast infiltration rates? Or maybe the soils are already high in certain nutrients. The Kentucky Division of Water's 305B assessments will help you understand if there are streams that have already been characterized as being impacted or noted for high quality and in need of protection. Geography is important. Headwater streams are often better to prioritize because you're not dealing with upstream contributions and can see impacts more quickly. Then you can work your way downstream for ongoing improvements. Stakeholder support is always critical. Is there local interest in protecting or restoring water quality? What are the local goals or special water interests, and do these align with the watershed planning goals? Or there may be local concerns that strengthen support, such as a pending development permit or a threatened water supply. Of course, available funds may make some watershed efforts easier. There may be related funding sources that can help pay for proposed BMPs, such as Farm Bill cost share programs that can help pay for agricultural practices. Or a proposed development project could incorporate BMPs such as stormwater retention basins. In this example on the slide, priority is given to the subwatershed that displays high pollutant yields, but also includes motivated stakeholders and a majority agricultural land use, which could reduce the types of BMPs that are needing to be implemented. The Priority 2 subwatershed has highest pollutant yields, but also greater imperviousness and may be more difficult to address. Priority 3 has lower yields and is already largely protected as a nature preserve. You can see that by evaluating the land uses of the watershed or at a subwatershed level, we can begin to target some best practices that will help us reach our water quality goals. This graph shows how various land use sources contribute to the overall annual phosphorus load, with WWTP standing for wastewater treatment plant, and a margin of safety, or MOS, is typically added to the load reduction goals in the TMDL report, providing a buffer for unknown sources or other goal satisfaction obstacles. In order to meet the water quality criteria, loads will need to be reduced and/or reallocated among the various land uses. While effectiveness at pollutant reduction can vary greatly, depending on a variety of localized factors, there are ways to estimate reductions for this evaluation process. In summary, once you have used the load and yield calculations to prioritize subwatershed areas for improvement, you can begin evaluating these areas for land use and likely pollutant sources. Then you can develop a list of associated best management practices that can be further evaluated and vetted for effectiveness and feasibility. Let's begin to look at some of the land use types and considerations, all of which can have differing impacts. In Kentucky, some of these land coverages include urbanization, crop and livestock farming, forestry, and mining. In the remaining presentations of this module, we'll cover management practices that can be adopted to address pollutant contributions from each of these land uses, and we will go into greater detail about the most common pollutants of concern stemming from these activities. One major land cover or land use factor to consider when evaluating watersheds is imperviousness. The fate of rain that falls on the land is strongly affected by the percentage of land cover that is impervious to water infiltration. So, imperviousness refers to the sum total of all hard surfaces within a watershed, including rooftops, parking lots, streets, sidewalks, driveways, and all surfaces that don't allow infiltration of rainfall into the underlying soils and groundwater. This graphic shows how less rainfall infiltrates the ground and more rainfall runs off as the percent imperviousness increases. Evapotranspiration also decreases with the increased imperviousness and fewer trees. In a forested or grassy area, shown in the top left, most rain soaks into the soil or infiltrates, where it eventually is used by the growing plants or percolates downward into the groundwater table, or it can re-enter the atmosphere through evapotranspiration through trees or other vegetation. With the increasing density moving clockwise around the graphic, less water infiltrates and more runs off to nearby storm sewers or natural streams, carrying pollutants picked up along its way. This is another graphic that further illustrates how changes in land cover and increasing impervious cover affect infiltration and runoff. Moving from left to right with the loss of natural vegetative cover, you can see the pattern of increased runoff and decreased infiltration. This generally results in stream flows that have high peak levels and lower low flows in between, as well as poorer water quality. In addition to increases in runoff amounts or volume, imperviousness also increases the speed of runoff and subsequent in-stream flows. Conventional urban infrastructure enables faster stormwater collection and movement to the nearest waterway, which often results in increased flooding, stream bank erosion, and stream bed scouring. These effects are of concern for both human infrastructure and aquatic habitat. Flooding and high flows can damage roads, bridges, buildings, and other infrastructure, and aquatic habitat can be scoured away, decreasing the presence and numbers of organisms that can survive. Another aspect of increasing urbanization is something called stream flashiness. As you can see in this diagram, increased urbanization and impervious surfaces lead to a faster, greater stream discharge response. In contrast, the forested watershed shows a more gradual, moderate rise in stream discharge after a rainfall event. Unless countermeasures such as stormwater BMPs are designed and installed, an urbanized area will likely flood more frequently and severely than before development occurred. In summary, imperviousness is a big deal because it causes all these negative effects on water quantity and quality. Less groundwater recharge not only impacts underground aquifer replenishment, but also limits base flows for surface streams during dry conditions. More runoff and erosion adds pollutants to receiving water bodies. Aquatic life habitat is often scoured away by high stormwater flows and associated flooding. And flooding becomes more of a problem when water bodies can't accommodate the increased flow volumes. Stream temperatures can increase when runoff water passes over warm surfaces on its way to the stream, and these higher water temperatures can result in lower dissolved oxygen concentrations and the potential for increased algal growth. To combat these effects, you may have heard of the movement from gray to green. This refers to the effort to move away from traditional concrete or gray solutions for water management towards solutions that include the use of vegetation to absorb and treat water runoff, or green solutions. These solutions are also sometimes referred to as green infrastructure or part of low-impact development. The images on this slide show green infrastructure to treat runoff from parking lots, roads, and sidewalks in the two photos on the left, riparian buffers to treat runoff from adjacent pasture and cropland in the top right, and a treatment wetland being used to treat runoff from residential development in the bottom right. As we talk through the various land use best practices, you'll note that many incorporate green infrastructure solutions. Now that we've covered imperviousness, let's talk about soil. Soil types affect water quality by how easily they erode, what else they contribute when they do erode, such as phosphorus that may be adsorbed to soil particles, and what types of land use they best support. Additionally, fine-grained soils, such as silts and clays, can become more compacted, reducing the ease of water infiltration and generating greater runoff rates. This chart shows how the USDA and the Soil Conservation Service rate 4 different soil classifications in relation to runoff and infiltration. The faster the infiltration rate, the lower the runoff potential, and vice versa. Group A consists of deep, well-drained sand and gravel soils that have higher infiltration rates and lower runoff. Groups B and C, with fine to coarse and moderately fine to fine soil textures, produce more runoff potentials. As you can see, the clay soils in Group D have much lower infiltration rates and thus greater runoff potential. Another important factor to note is that when development occurs and soils are disturbed, compacted with bulldozers, and the topsoil removed, infiltration is likely to be much slower and runoff much greater. We'll be discussing ways to determine watershed soil types for your area of interest. The geology of the state of Kentucky can also have a profound effect on water quality and water movement over, under, and through the land surface. The subsurface will affect the chemical characteristics of the water, its drainage patterns, and the groundwater surface water interactions. Karst geology refers to topography formed from the dissolution of rocks by slightly acidic water moving through it. This creates underground drainage systems and can greatly influence groundwater flow paths and the associated travel of pollutants to surface waters. This map shows the karst regions of Kentucky. The darker blue areas are highly karstic and the lighter blue areas are less karstic. The karst topography of Kentucky is mostly due to limestone bedrock, but some is also found on dolostone. Geological features also influence the land's topography or surface features and the types of land uses in those areas. In Kentucky, cropland farming tends to occur mainly in the flatter bottomland areas of western Kentucky. Farmland in the central bluegrass region is utilized more for livestock production and urbanized areas. And the mountainous terrain of eastern Kentucky has historically been used for logging and mining and less so for agriculture. In order to assess these watershed features so that you can further evaluate and prioritize your water improvement efforts, there are many online and other resources. The simplest option may be just using Google Maps or Google Earth. It's a free, useful tool to scope out satellite imagery of your watershed area and begin to identify prevailing land uses and possible pollutant sources. The National Land Cover Database is developed by the USGS and other partners and provides updated land cover information on a national scale, including imperviousness. Watershed is a watershed modeling web app that provides an easy-to-use interface for finding a variety of helpful information. We'll be delving into this tool next. Local zoning maps can help watershed planners evaluate potential or likely changes in land use by showing where development is likely to occur, such as in residential, commercial, or industrial zones. The Kentucky Infrastructure Authority portal is a useful tool for learning about local drinking water and wastewater systems and where cities and towns may be planning for infrastructure improvements or expansion. Map coverages from the KIA and regional area development districts can also help determine sewered versus non-sewered residences. The US EPA's ECHO database, or Enforcement and Compliance History Online, helps you find permitted point source discharges and track their compliance history. The USDA's National Agricultural Statistics Service provides a variety of data related to crop production and livestock types and numbers by county. And U.S. Census data can be helpful in discerning population concentrations and the income and education levels of residents. All this information can be helpful when you are prioritizing subwatersheds and selecting BMPs. As I just mentioned, you can search it for a location on Google Maps, then zoom into areas of interest to better understand the lay of the land and the various land uses in the watershed area. In this example, you can see that we zoomed into the area just northeast of Bardstown. This is within the Beach Fork watershed. A large stone quarry there could be contributing to sediment loads, metals, or high conductivity levels in nearby tributaries. It's also likely to generate a lot of runoff from all of its exposed bedrock areas. You can also use Google Earth to search around your watershed and become more familiar with its distinguishing features. And later, you can mark sites for potential BMP locations that can be reviewed by local residents for feasibility and other considerations. This example from the Whitesburg area in Letcher County used different colored pens to mark possible locations for riparian plantings in green, stream bank stabilization in yellow, stream restoration, mine remediation, and other BMPs, such as step pools and retention basins in pink. I also mentioned the National Land Cover Database, which is hosted online. This interactive viewer provides broad coverages of land types for the state. The legend of the graphic on the slide, if Kentucky, shows all the possible land cover types, including wetlands, crops, which we see more of in western Kentucky, pasture and hay in yellow, which we see more in central Kentucky, grasslands, forests in green, which is more in eastern Kentucky, barren land, and developed land, shown by low, medium, and high intensity in red. This viewer is helpful, but the data is also incorporated in the Wiki Watershed tool, which we'll discuss next. Wiki Watershed, or modelmywatershed.org, enables anyone to analyze land use in their watersheds. During the following activity, we'll walk through the tool visualizations for each of the characteristics listed here: streams, land, soil, terrain, climate, point sources, animals, and water quality. In addition to providing details about all of these features, Watershed also allows users to model stormwater runoff and water quality impacts using professional grade models and compare how different conservation or development scenarios could modify runoff and water quality.